In this video, I'm going to show you how to set up the partial fraction decomposition for a rational function. Before I show you how to do it, let's go over what are the different scenarios you might run into. So you might run into linear factors in the denominator. Sometime you might have linear factors that are repeated, or sometime you might have irreducible quadratic factors, or same thing, quadratic factors that are repeated. Another case would be when you have an improper fractions, you might have to do a long division first before you set up the partial fractions. So the last part, I'm going to leave it for another video so you can watch it another time. For now, let's take a look at the first four cases. And before that, here's a little idea behind why this method works. So suppose I give you these fractions. Say you're given 1 over x minus 3 minus 1 over x plus 1. So in order for you to combine this, you will need the least common denominator, which would be x minus 3 times x plus 1. So you would multiply each fraction by what they're missing. So this one you would multiply by x minus 3, this one x minus 3 top and bottom, and this one you would multiply with x plus 1 over x plus 1. So once you do that, your numerator becomes x plus 1 times 1 minus x minus 3 all over x minus 3 times x plus 1, which can be written as 4 over x minus 3 times x plus 1, or you can say 4 over x squared minus 3x and then plus 1x, that's minus 2x, and the last term you get is minus 3. So what we initially started with was these. Those are our partial fractions, and when you combine, you get something like this. So in other words, we can see that 4 over x squared minus 2x minus 3 is equivalent to 1 over x minus 3 minus 1 over x plus 1. So the idea is to actually do the opposite of that. So we're going to start from here. That's how the question will be presented to you, and you have to decompose into something like this and something like this. So you'll set up your simpler fractions with the bigger fraction that's given to you. So let's illustrate how this is going to work with the first problem I have here. So it's a proper fraction, so we can go ahead and factor. So let me clear this up first. So we can go ahead and factor the denominator, which it is. In this case, it's factored. So I can write it as following. This is 5x minus 13 over x minus 3 over x minus 2. So you break this up into two fractions. So the denominators are these. So you'll have two linear factors. You'll have x minus 3 and x minus 2. Now what goes on the numerator is 1 degree less what you have in the denominator. So if it's linear here, that means it's going to be 0 degree on top, which is a constant. And the second one, same thing, linear here, you'll put a constant on top. Now to make that constant different from previous constant, we're going to label it b. So that's your setup for partial fractions. And now you need to solve for what are these constants. And then you're pretty much done. So let's go ahead and do that for first problem, and then the rest I will just set it up for you. We really need to just work out the algebraic work here. So I'm going to go ahead and multiply both sides by the LCD, which is this denominator. So you'll have 5x minus 13 on the left side when you multiply by the LCD on both sides. And on the right side, you'll have a times x minus 2 because this will cancel. And for b, you'll have b times x minus 3. And then you work it out algebraically. We're going to go substitute some values because we're solving for a and b, so it'll be easier that way. I'm going to choose x equals, let's pick x equals 2. So then your left side is 5 times 2 minus 13. And on the right side, this is 0. So that's why I chose x equals 2. So b times 2 minus 3, that's going to be b times negative 1. So we have 10 minus 13 on the left side, that's negative 3, is equal to negative b. So we know b is equal to 3. All right, so we found b. Now what about a? So for a, I can make this go to 0. So I'll pick x to be 3. So that gives me 5 times 3 minus 13 equals a times 3 minus 2, and the second part will go to 0. So this is 15 minus 13, that's 2, is equal to a, because 3 minus 2, that's 1. So there you have your constant. So this fraction that we came up with, the constants are a is 2 and b is 3. So these are the partial fractions for this problem. So let's set up the partial fractions for this one, and we're not going to solve for our coefficients here. We're just going to set it up. So I will have to factor this first. It's proper because degree on numerator is 1, degree on the denominator is 2. So we can write this as 5x minus 7 over, and the denominator can be factored into x minus 2 and x minus 1. So I have linear factors in the denominator. So I have 2 of those. You have x minus 2, x minus 1. On the numerator, you're going to put a and b. So that's your setup for this problem. The rest is solving. So I will leave that up to you. Algebraically, you can solve for a and b. So here's another one. So we see degree on top is a 2, degree on the bottom is a 4, so it's proper. Let's go ahead and factor. We have x squared plus x. You don't have to factor the numerator, just the denominator. So I see a degree 4 and a 2, so I can factor this into the following, x squared and x squared. And then the next terms, I can put negative 4 and plus 1. So let's factor this one a little bit more because that's the difference of two perfect squares. So this is equal to x squared plus x over x plus 2, x minus 2, and x squared plus 1. So x squared plus 1, this is it. This doesn't factor further on the real line. So this can be decomposed into the following. So since I have 3 denominators, I need 3 smaller fractions. So here's first, here's the second, here's the third. So I will write one with x plus 2, another with x minus 2, and this one with x squared plus 1. So remember, what goes on the numerator is 1 degree less. So here I'll put a constant, here I'll put another constant. But for the third one, since on the denominator is a quadratic, on the numerator, you're going to put a linear function. Linear functions are mx plus b or ax plus b. So since I already use a and b, I'm going to go with cx plus d. So that's a generic linear function. And then the next thing would be to find our constant a, b, c, and d. So I'll leave that up to you. Pretty much you multiply both sides by the LCD, which is this right here, and then figure out your coefficients a, b, c, and d. So here's another problem where we had a linear combination of quadratic as well. We're going to set up the partial fraction. Now for this one, be careful. This is z to the second power. So think of it as it's a repeated. It's z times z, or I can think of this as just z squared. So it's a linear factor, but it's repeated twice, so it has multiplicity of 2. So we're going to actually write down 3 fractions for this. So one of them is z, the next one is going to be the z squared, so that's for all of these. So you always count up to the multiplicity. And then the last one is the linear factor, another z minus 1. And now on the numerator, this is a, since denominator is linear. This is b. Now you might say the denominator is quadratic, but it's not. It's actually this one that you're looking at, which is z, and it has a multiplicity of 2. But the factor, the parent function you can think of is just linear function. So in the numerator, we put b, constant function. And z minus 1, again, that's a linear factor, so this will be c on top. So there you have your partial fraction set up for the next one. Here's our last problem. We're going to set up the partial fractions. So this is already factored, so I'm going to go ahead and set it up. So I have a quadratic here with the multiplicity of 2. So I'm going to write 2 fractions for that. I have a linear here with the multiplicity of 3. So I'm going to write 3 fractions for that. So a total of 5 fractions. So 1, 2, 3, 4, 5. So first, let's start with the quadratic. So you have x squared plus 1. So that's one factor of that. And then x squared plus 1, the second factor. So on the numerator, we're going to put the linear functions because it's 1 degree less, ax plus b, and this is also cx plus d. Then we have x minus 2, multiplicity of 3. So we're going to write x minus 2 first, and then x minus 2 squared, the second factor, and then x minus 2 to the third, counting up to the multiplicity. And on the numerator, we're going to put linear factors because this is linear. So we will have, so we already use A, B, C, D. So this is E, F, and G. So that's how you set this up. And then the next is just finding this coefficient. So I hope the idea of setting up the partial fractions with a known constant, that's easy enough. I'll see you next time.